Today our discussion comes from the last section of Chapter 1, so Section 1.8, Solving Absolute Value Equations and Inequalities. We will be taking a lot of the information and review work that we did in the chapter and applying it to absolute value equations and inequalities. You can see the student learning goal today. Let's start with some basic absolute value discussion. If we want to solve absolute values algebraically, we want to think, let x be any real number. If my x value is greater than or equal to 0, then the absolute value of that number is the number itself. Example, if the absolute value of 5 is what I wanted, I would get 5 out. The absolute value of 7 would be 7. The absolute value of 0 would be 0. The absolute value of 2.5 would be 2.5. Any positive number's absolute value is equal to itself. Whereas if x is less than or equal to 0, then the absolute value is equal to the opposite of that original value. If my number is -2 and I take the absolute value of -2, I get 2. If I want the absolute value of -4, it equals 4. Each time I've taken the opposite of what I started with. If I want the absolute value of 0, then I'd have to take the opposite of 0. Well, the opposite of 0 we know is 0 itself. 0 is the only number who has itself as its opposite. Geometrically, when we think about absolute values, we want to think about it is the number's distance from 0. Distance is always a positive measurement. You cannot ride -5 miles. You say, oh, well, I can put it in reverse, I can go backwards. You still have traveled 5 miles. So geometrically, we're talking about distance, the measurement. And that has to be positive. So if we were to solve an absolute value basic equation, you would look at something like this, where we say 2x minus 1's absolute value has to equal 3. So you'd be thinking all the numbers that are inside this absolute value bar that will make this true have to come out to be equal to 3. So brain says if I do that, all the possible numbers could either be one of two things. Because right now, with the block on it, and not seeing what's underneath there, I know if this was positive, this could be a 3. I know this could also be -3 and be true. Because equations, positive and negative numbers, absolute values come out to be 3. So if you do that thinking and say, whatever's underneath here could be equal to a 3, or whatever's underneath here could be equal to a -3, it doesn't matter the size, the complexity of what's underneath there. Those are the two things you need to analyze. So again, taking this away, if we say what's underneath here could be equal to 3, so then I'm going to say in my mind, well, that means 2x minus 1 could be equal to 3. But I also said that 2x minus 1 could be equal to -3. So we're really getting two possibilities to make this true. So if you solve both of those equations, add 1 to both sides, we would get 2x equals 4, divide by 2, x equals 2. And over here, if you add 1 to both sides, 2x equals -2, divide by 2, x equals -1. In order to show that on the graph, because they are equalities, we would just need to graph those points. So I'm going to graph a -2, a -1, 0, 1, and 2. Equally spaced so we don't have any gaps in our graph. x equals 2, I place a dot at 2. And if x equals negative 1, I place a point at negative 1. And what that means is, again, those are the two values that would make this true. If we checked mentally, put a negative 1 back in, right here, into your equation, do the math. 2 times negative 1 is negative 2. Negative 2 minus 1 is negative 3. The absolute value of negative 3 is 3. And then second time, put a 2 in. And 2 times 2 is 4. 4 minus 1 is 3. The absolute value of 3 equals 3. So you've found the two values that make this statement true. Now, if we talk about absolute value and inequalities, there is a slight difference here. Very similar in terms of, yes, we have this range of numbers rather than a single number because they are less than or greater than relationships. So if we start with, if A is a greater than 0, so we're thinking, okay, it's a positive number, and the absolute value of x is less than that positive number, then x has to be greater than the opposite of A, and x has to be less than A. If A is positive, again, A is greater than 0, and the absolute value of x is greater than A. So the only difference here now is the less than or greater than. We would get x is less than the opposite of A, or x is greater than A. So let's just start thinking, and let's take, as an example, maybe let's bracket this off and just think about this to start with. If we were looking at just this top inequality, give me all the values that are less than 5. So a lot of you started thinking, all the values that are less than 5 would be 5, 4, 3, 2, 1, 0. So all the values less than 5, I'm going to do like an open circle here, and I'm going to go everything this way. But then again, people would say, well, wait a minute. Couldn't I use negative 5? So if we reset that, and again, we're just doing this. So right now we're thinking, okay, x is less than 5. So we said 5 wouldn't work, but all the numbers like 5, 4, 3. So we're thinking 5 wouldn't work, but we're thinking all of these. Well, and if I kept going that way, what other numbers? Well, x is less than could also be, what about a negative 3? If I take the absolute value of negative 3, hey, that would work. What about a negative 4? Oh, that would work. What about a negative 5? 5 is not less than 5, so we would have all the numbers to the left of 5, but then all the numbers to the right of negative 5. So we would have this range in here that would make this true statement. So look at it real carefully. Those then turn into all the numbers that are greater than the opposite of A, and all the numbers that are less than A. I like to say we kept the original statement. All the numbers that are less than A matches all the numbers that are less than 5, and we took x, switched the sign, switched the value of the number. And it is an and, so we're graphing the intersection, both, okay? If we would think about the greater than 5 situation, so now we're here. If x is greater than 5, well, most people right away are saying, okay, you can't have 5, but you can have 6, 7, 8, 9, 10, all the way to infinity. Then you also need to think about, wait a minute, what other numbers would work? Well, what if I had negative 5? Negative 5 is 5, that's not going to work because it's greater. What about a negative 6? A negative 6 with the absolute value would be a 6. 6 is greater than 5. What about a negative 7, negative 8, a negative 9, a negative decimals, fractions in there. But again, we're looking at greater than. So look at this one. If x is greater than, on your original inequality, we are saying you would take the original inequality, inequality, so all the values greater than A, so greater than 5 we did, and then the other piece comes from, it's all the values from our X position, which in this case is less than the opposite of that value. And it's an OR statement, because look at what type of graph we have. We have two separate pieces, they do not touch, they do not overlap. So we like to start thinking in this realm that if we have an inequality, it's X is less than A, we want to start thinking that's going to be an AND situation where we have greater than or equal to A, that's going to be our OR situation. And that would be the inequalities in their original position. So, if we were to solve an inequality and graph it on the number line, brain-wise, again, you could use the little trick we did on the last one, saying, okay, wait a minute, how do I start this? Think of it like this. Any number inside of there has to be less than or equal to 8. And it's less than or equal to, so I'm going back up here, less than would match the top inequality. And so I want to think whatever's underneath there, and we know it's 5x plus 2. So if we start writing, 5x plus 2 could be less than or equal to that original value. And, because it was a less than to begin with, and whatever's underneath there, so 5x plus 2, would also have to be, switch the inequality sign, greater than or equal to, change the number to its opposite, and you would get your other solution. If you solve both of these separately, like we've been doing, you should get your solutions. Remember, these are inequalities. So 5x is less than or equal to, in this case, it looks like a 6. So x is less than or equal to 6/5. 1.2 if you like the decimal form. Over here, subtract 2 again as well. 5x is greater than or equal to -10. Divide by 5. X is greater than or equal to -2. On your number line, you'll notice your solutions do not have the same number as your base, so just make sure you include them all when you're doing your graph. So if we graphed up here, I have to write over my other numbers slightly. If we graphed equivalencies, so maybe we would do -2, -1, 0, 1, and 2. And it's an and, so I'm thinking intersection, overlap. I need all the numbers that are greater than or equal to -2. So I'm thinking greater than or equal to, solid, and I'm thinking everything to the right. But for x less than or equal to 6/5 would be just about 1.15, 1/5, 1 1/5, so 1.2, we'll approximate it right there. And that's everything that's less than. So if I'm down here and I'm everything to the right, and if I'm here and I'm everything to the left, we have to be able to shade and the intersection, which would be this interior portion only between those two values. So there would be our inequality solution to this compound, because you have the two statements that came out of the absolute value graph. Same rule, same property I'm referring to, but now we have a greater than situation. So if we have a greater than situation, you can use your thought process again. Hey, whatever's underneath here is going to be greater than 4. So you're thinking, the absolute value. Whose absolute value is greater than 4? Well, 4 isn't, but 5 is, and 6 is, and 7 is, and 8 is. And we turn it around going to the negatives. Well, that would be the -5, the -6, the -7. So you need to start saying, all right, I got two situations here. And And those two situations are the inequalities you write down. So we're going to follow the property this time for a greater than situation, which is the bottom one. And we're going to start with keeping the original as is. So we'll take 3x plus 2 is greater than 4. Or, second part, 3x plus 2, whatever's underneath that blank box, has to be the opposite sign, opposite value. So now again, if we solve both of these, 3x is greater than 2, divided by 3, x is greater than 2/3. Over here, 3x is less than -6, divided by 3, x is less than -2. Again, we do not switch the inequality sign because we were not dividing by a negative, we were dividing by a positive. So our solution this time, statement reads, x is greater than 2/3 or x is less than -2. On your number line, place values around it. You can see we need some negatives, some positives, and again, it's an or statement, which means both situations must be graphed. So x is greater than 2/3. Well, 2/3 is about here on your number line, greater than everything to the right. And then we have x is all the values that is less than -2. So it's an open circle at -2, less than is to the left, and we have that solution. So we have compound inequalities and or absolute values. Come with any questions about these examples for discussion, and we can practice the problems for this section as well.